Dear students, today I am giving the sixth video on topology. We start with the intermediate value theorem. Statement: let X2 be a connected topological space, let f from X to R be a continuous function, and a, b, and x be such that f of A is less than f of B. Let d element of R be such that fa less than d less than f of B. Then there exists C in X such that f of C equal to D. That is, D is the image of C under F. We can go through the proof of it. Here X is connected and F is continuous. Implies f of X is connected. Moreover, f of X is subset or equal to R. What does it mean? F of X is an interval. That's what we have proved in last class. Now f of A, f of B, elements of f of X, because we are discussing about an interval in such a way that f of A is less than f of B, so that you are getting the interval fa of B directly. This implies the interval closed interval fa of B is subset or equal to f of X. And when we are taking intermediate value d in between f of A and f of B, again f of A less than d less than f of B implies d is an element of fa of B, closed interval fa of B. That means d is an element of f of X. And f is a continuous function. Of course, we can conclude that there exists a C in X in such a way that f of C equal to d, that d is the image of C under F. That is what is the intermediate value theorem. It's an important theorem. Study well that one. We can discuss one more theorem, that is statement that X2 be a topological space, and suppose that X equal to A union B, where A and B are non-empty subsets of X such that A and B are separated in X. If capital H is a connected subspace of X, then H must be subset or equal to A, or H must be subset or equal to B. That is what the statement. You can go through the proof of it. Proof we can discuss. What is given that X equal to A union B, where A and B are non-empty subsets of X that are separated in X. Then what you get? It implies A and B are both open subsets of X, because the definition of separation. And we can use the previous theorem, what we have proved in last class. So A and B are both open subsets of X, we are concluding. That means A intersection H and B intersection H are open in H. Also, they are intersection, that is A intersection H, intersection B intersection H. What is that? A intersection B intersection H. It is phi intersection H is equal to phi. Because A intersection B equal to phi, because A bar, that is closure of A intersection B, is phi. Moreover, the union A intersection H, union B intersection H, that's equal to A union B intersection H. A union B is X, or X intersection H, that's what H. So, if A intersection H is not equal to phi and B intersection H is not equal to phi, then clearly A intersection H and B intersection H will form a separation of H. But what is given already? The statement H is connected. So, this way we cannot argue that is A intersection H not equal to phi, B intersection H not equal to phi is not correct. So, A intersection H must be equal to phi, or B intersection H equal to phi. This implies H is subset or equal to X minus A, because A intersection H equal to phi, or H is subset or equal to X minus A, or H is subset or equal to X minus B. Or we conclude that when H is subset or equal to X minus A, that is H is subset or equal to B. Other case, H is subset or equal to A. That's what the proof of the theorem. Coming to next theorem, statement, let X2 be a topological space and let A tau A be a connected subspace of X. let B be a subspace X such that A subset or equal to B and B subset or equal to A closure. Then B tau B, the space B tau B is connected. We can discuss the proof of it. That is, if possible, let B tau B is not connected. You argue like that and arrive at a contradiction. This implies B has a separation. B has separation means B equal to, B can be written as C union D, where C and D form a separation for B. Now A is subset or equal to B implies A is subset or equal to C union D. Since A is connected by the previous theorem, A subset or equal to C or A subset or equal to D. First consider A subset or equal to C, that is suppose A subset or equal to C. This implies A bar subset or equal to C bar, but B subset or equal to A bar. Therefore what you get, B subset or equal to C bar. Now C bar intersection D equal to 5 and C intersection D bar equal to 5. This implies B intersection D equal to 5 because B is subset or equal to C bar. So we get a contradiction now, which is a contradiction to the fact that D is a non-empty subset of B because B equal to C union D. Hence our assumption is wrong, or B tau B is connected. Now we are discussing a question. Let tau be the lower limit topology on R, whether R tau is connected. Justify your answer. Solution: consider the interval semi-closed open interval AB. It is open in the lower limit topology on R, being a basis element. Now, complement of closed interval A open interval B, that is semi-closed open interval AB. So, what about its complement in R? That is minus infinity A open interval union semi-closed open interval, that is B infinity. Here B infinity, interval B infinity equal to union of intervals Bx, where x is always greater than B. Clearly it is open in the lower limit topology. Since lower limit topology is finer than the usual topology on R, we see that minus infinity A is open in the lower limit topology on R. Complement of closed open interval AB in R is open in R with respect to the lower limit topology. That is what the conclusion we are getting. So its complement in the sense closed open interval AB is closed in R. The complement is open, that is, it is closed in R with respect to the lower limit topology. Thus, R has a non-empty set which is both open and closed. This implies R with lower limit topology is not connected. One more theorem. Let X to be a topological space and A subset or equal to X, then the following conditions are equivalent. First condition, A, the subspace A tau A is connected. B, the set A cannot be expressed as the union of two non-empty sets that are separated in X. And part C, there does not exist UV elements of tau such that U intersection A not equal to phi, V intersection A not equal to phi, U intersection V intersection A equal to phi, and A subset or equal to U union V. Then the proof style, we are proving this in the sense that this is style A implies B, B implies C, C implies A. In that way we are proving. In each case we prove the contrapositive of the implication. First we discuss A implies B. Suppose that A equal to union V, where U not equal to phi, V not equal to phi, U bar intersection V equal to phi, U intersection V bar equal to phi. U bar is the closure of U in A. Clearly U and V are non-empty subsets of A, and we are considering U bar intersection A intersection V, that is U bar intersection A intersection V, That is u bar intersection v, because v subset or equal to a, that's equal to phi. Similarly, u intersection v bar intersection a, that's again phi. Hence u and v are separated in a, and that a is not connected. Next, b implies c. Suppose Rx is uv in tau such that u intersection a not equal to phi, u intersection v, u intersection a not equal to phi, v intersection a not equal to phi, u intersection v intersection a equal to phi, and a subset or equal to u union v. Clearly, u intersection a and v intersection a are non-empty subsets of a. You are taking their union, that is u intersection a union v intersection a, that is u union v intersection a. Here a is subset or equal to u union v, therefore this intersection is a. We have to prove that u intersection a and v intersection a are separated in X. So consider u intersection a closure, intersection v intersection a. Taking an element there, small x is an element of u intersection a closure, intersection v intersection a. What does it mean? That is, x is an element of u intersection a closure and x is an element of v intersection a. This implies x is an element of u intersection a closure and x in v in tau. Which implies u intersection a intersection v not equal to phi. A contradiction to u intersection a intersection v equal to phi. That is, u intersection a closure intersection v intersection a equal to phi. Similarly, u intersection v intersection a closure is again equal to phi. Hence, u intersection a and v intersection a are separated in X. Next part, next proof, C implies A. Suppose that A to A is connected. This implies the X is non-empty disjoint open subsets u dash v dash of A to A such that A equal to u dash union v dash. Now u dash v dash elements of tau A implies u dash equal to u intersection A and v dash equal to v intersection A for uv elements of tau. Actually, that is nothing but the subspace topology I discussed earlier now. So u dash not equal to phi implies u intersection A not equal to phi. V dash not equal to phi implies v intersection A not equal to phi. Therefore, phi equal to u dash intersection v dash. What is u dash u intersection A? V dash is v intersection A. So their intersection is what, phi, or u intersection v intersection A. Now A equal to u dash union v dash, that is equal to u intersection A union v intersection A, that is u union v intersection A, which implies A is subset or equal to u union v. Hence the proof is completed. And that's all about this section. It is topology 6. Go through it well, and any doubts means just mark it down. We can discuss in the class.